All right, so now we have Jan Paul, who's going to be talking to us about typing in Scheme.
Okay, so hi, I am Jen Paul. You probably have seen me doing AV here, and I just failed at doing AV for myself, so that's fun. But I actually do research, believe it or not. So I'm going to be showing something I worked on during the summer. So as a quick caveat here, before this I didn't really do any Racket or Scheme. This actually just came as a side effect of another project I was working on, which I'll touch on a bit, but since it's out of scope, I won't really go into it unless people have questions about it. So yeah, as this being more of a position paper, I want to know exactly how this community feels about this sort of default type setting I've been working on. So let's get started. Okay, so we can start with an example. And the idea here is that we want to be able to identify from the programmer's perspective what they believe is going to happen in their code versus the probability of something happening in their code in a quantitative sense. So we have this example here. So this is a load balancer. Normally here, we're given a latency measurement from a service instance, and then it's going to compute a composite health score by combining the average latency with the failure rate, what's happening there at the top. So here, we're using trimmed to ignore outliers. So this means that it's going to drop the top and bottom 5% of measurements to avoid any skews on occasional spikes or timeouts. So what happens here is that service instances collect buckets of the timing data, and you have certain beliefs about these buckets. So under normal operations, we can have hundreds of samples per bucket, and alpha is a tuning parameter. So in this case, if alpha is 0, we only care about latency, whereas if alpha is 1, then we only care about the failures. And then the monitoring ensures that the buckets are never empty. So the obvious issue here is that edge cases can exist. So small buckets during startup, you can also have misconfigured alpha values. And this trimming step here is going to be the tricky part to try and get a sense of what we believe about it. So if we take a sorted list and drop k elements from each end, and then compute the mean, then this can fail if the list is empty, for example. So this is a basic check you want to make. So this is a mental model that the programmer has before we even start to think about the objective nature of the list, that it shouldn't be empty. By that I mean a programmer might think, okay, we have 100 plus samples, so trimming is safe in a quantitative sense. We rarely get small buckets and need guards. And the buckets should never be empty because of monitoring, because monitoring ensures collection. So what we want to be able to do here is give some flexibility to the type system to encode these three different beliefs that I've described. So instead of just saying, okay, there's going to be a binary of this will work or this will not work, statically speaking, we want to be able to express a very kind of hand-wavy notion at first of this usually works, or this is an edge case I don't want to optimize for, without having to add expensive runtime checks everywhere. So yeah, these are some traditional approaches. And so the trade-offs here aren't necessarily bad. I wrote bad there, but they're not necessarily bad trade-offs. They're just trade-offs that you wouldn't really want to deal with in this specific mindset. So you don't want to add runtime overhead, and annotation burden kind of would defeat the point here, although ideally this would be the most formal case. We're dealing with programs and beliefs that are very simple and compositional in nature, in that you don't really want to spend so much extra time developing on this meta annotation language. So we want to try and simplify it as much as possible while maintaining some static guarantee. So, oh yeah, and then ideally then optimize the generated code for this common case. So what does this look like then? These are the plausibility rank types. So these are completely annotated by the programmer. And in this case, for this example, I've annotated a couple of them you can see. So rank 0 is going to be the normal case, in which you have a list of length greater than 20, and in which alpha exists in the normal domain you'd expect it to. But then here, and you can see this here, you can see my mouse. Yeah, you can see this here in the assume default. What's happening here is that the programmer is actively, explicitly annotating what properties are going to assume to hold in the cases. So here, there's nothing being checked at runtime. This is completely relaxing the type system in a way that we are literally trusting the programmer's intent for what they believe to be an unusual case or an exceptional case. And then what you should annotate as a type error, which is the case here, rank infinity. So this is going to be a rank that you can never possibly reach. Ranks in which everything will definitely fail. So type checking will definitely fail if n equals 0 in this case. So how do these cases actually get implemented? I'll skip through that for a second here. Okay. So this is the policy table. And so this P table is going to be working with the typing rules that are implemented. This is in, if I go back here, that this is the overall architecture of everything. So you have the rules in turnstile. And so you have these, this assumption rule that's going to work in tandem with the subsume of the policy table for these operations. And this is what's defined on a program case-by-case basis for the for that particular program or for that particular program. So assume default introduces plausibility assumptions. So this is the keyword here on plausibility. So yeah, we extend the environment with variables at rank 0, the normal case, and these have now been formally declared as a normal operation. In the primitive rule, we check all arguments and get their ranks, and then we look up the operation's base rank from the policy table pi, and then the result rank is the maximum. So it's going to be the weakest link principle here. So that means that if any sub-expression needs exceptional assumptions, the whole expression does. And then this works as kind of a safety chain here. And so the policy table here is going to be very domain specific to whatever you're operating in. And then this just serves as a map. So you can think of in division in general can have rank 1. That means that it might be 0, but it's unusual. It still needs handling, something of this sort. So if I can go back here, hopefully that clarifies a bit how much trust we're putting on the annotations to try and just weaken type checking and just get your program running. So this might seem a bit bizarre at first, but then what I mentioned at the beginning of how I came to this kind of path here is that this works as a way to introduce a gradual probability. And by that, what I mean is, I won't go into it super in depth here, But I have an actual refinement here via an abstract interpretation that essentially gives me the tooling necessary for whenever a programmer writes these qualitative beliefs that they've specified. Again, this is very just trusting the person programming. Whenever you get actual quantitative information, so this can be later on, so you can say in an example in which you would need to know what percent a certain package might have, what percent of dropping a certain package might have in a network or something like that. You might not have this information immediately, but you can write a qualitative belief about it. And so the idea here is that we create these partial orderings, which I'm not going to go into exactly here, but once you have these orderings, which are defined in the assumed default, then once you discover these probabilities in whatever way, you can actually gradually replace the qualitative notion with an actual formal guarantee of a probabilistic guarantee. And if the probabilistic guarantee doesn't hold, like if you said that an event A is at least as plausible as an event B, but then the actual numbers you got don't match that, then that's actually going to fail. So this is the main domain in which this sense of relaxing the type system, I believe, makes sense. And so we can now go real quick to the constraint solving and error reporting. So this is now going back more a bit into the relevant to Racket here. So for the constraint generation, so for each operation, we generate some inequalities. So when we see the vision, we look up in the policy table and we see what has been defined, and then we generate some constraints. So then the result rank is at least as bad as its dependencies. Then we have a lexicographic minimization using priority ordering. So then we first reject any rank infinity, so any type errors, and then we minimize to the maximum rank. So in our previous example, it would be rank 2, and then we go to rank 1, and then finally rank 0. So then the idea here is that we want to encode, we want to be able to encode this with the exponential weights. So that we know that a rank 2 actually outweighs a rank 1 meaningfully. So then, yeah, this is the tooling that ensures us to find the most plausible typing, not just a valid typing. And then finally, we have error reporting. So then, this is like the most concrete thing you can get out of this in this, at least in Racket, I believe, is that you can get some relatively nice errors, I think. So then when you have a constraint failing at rank 0, then we just trace back and we can, D3 constructs the counterexamples showing the concrete inputs that violate them, and then, yeah, we get the, which assumptions were actually too optimistic, concretely. Yeah, so then this is the safe execution. So this is what it looks like in practice for what I had shown previously. And yeah, the idea here is that the compilation overhead is minimal. So yeah, here we go. And then, so this is a quick why this matters table here. So just trying to understand where this fits in the context of all other approaches here. So the idea really here is to try to annotate beliefs without having to examine actual information at runtime, and then give a gradual path to be able to formalize these qualitative beliefs quantitatively. And then Racket and turnstile here are pretty nice because I can just do this via macros. So I don't have to implement a whole separate interpreter for this. So there are some limitations here. So the current limitations on this are for module boundaries and higher order functions don't really work. So this doesn't work modularly yet because I'm not really sure how to get that working. But yeah, so here are the next steps. So yeah, what we want then is to be able to get this good enough typing system working. And then there's two possible directions: either look more in this Racket domain and try and make actual usable programs, or also trying to go into any other any other domain in which qualitative information would be useful, and you would want to replace it with quantitative information at the end. And yeah, generate optimized code that works on what are the programmer beliefs. And yep, that is it. Yep.
Thank you very much. I think we have a question in front and then back.
Okay, thanks. This is interesting. My sort of thinking about this is, could this be used in other languages for something like function specialization, like saying, okay, well, this is the common case. 0, 1, and 2, the parameters 0 and 1 and 2 for this function are the common case. So to sort of give a hint to the compiler that, yeah, we need function specialization for those cases. Just like just-in-time compilers sometimes do that. This is a common case. Let's aggressively optimize for that. Would that be a thing that this could be used for?
Yeah, that would actually be. Yeah, that'd be pretty good. So I gave again the idea here is also trying to get ideas as to what domain this could be useful in. I gave this talk about 2 or a week and a half ago, and somebody suggested this as well. Yeah, this seems good. I haven't done any technical work to try and explore this more, but yeah.
And usually we don't, compiler writers usually don't trust the programmer, which is sort of
I love this work. I'm actually not convinced that what you're doing is a form of radical typing, because I think the way
I'm not convinced either, to be fair. I'm not convinced either, to be fair.
Yeah, well, because the way I see it is what you're really doing is you're relaxing what the progress theory means. So we did an honor paper 10 years ago on what we call progressive types, which is basically the idea. I view this as like a really nice generalization of progressive types. In our case, we just did it across the board, so we didn't have to worry about the modularity problem because you were just reducing what the progress theory gave you on all modules right, across the code base. Your problem is you're trying to do this at a more fine-grained level, and so you have to worry about module boundaries and stuff like that. But it's really about progressive weakening rather than about, and in fact, it's funny because your paper has this type racket example. I think like everybody who runs into type racket is inspired to write papers because it's like, how do you make anything work here, right? It's just so clever and complicated that numbers in type racket. So I'm just curious if that resonates with you, or whether that's at all a reasonable way to think about this.
I mean, yeah, it definitely does. So this is kind of a Frankenstein of a project in terms of the motivation for it, to be fair. So initially, the core motivation for this is to be able to solve. So this is what I didn't get into for the sake of scope, but it's to be able to solve. How do I say this? Probabilistic paradoxes. That's like the super specific domain. So this can immediately counter like the lottery paradox. So just super quick, in the lottery paradox, so you have a lottery where there's 100 tickets, and then you can have an assumption that any ticket has a 99% chance of being the losing ticket, but if you follow that conjunctive belief, at the end, you believe that every single ticket is going to be the failing ticket. And so this domain can let you encode that problem with partial ordering to fix that. And then, so because of that motivation, I think that general like philosophical thought is like a general, like you said, not an issue, but like a problem you encounter a lot. in typing in general. And now I'm trying to pull that down.
Any other questions? All right. Let's thank the speakers again.